you're about to see will be a whirlwind tour of some of the most advanced things you can do with the Scala type system if you really want to. And I'm going to go super fast, I'm afraid. It's going to be a very, very quick overview, which will include a lot of tantalizing hints at fun things you could be able to do, and only a few details. People often say to me, in a half-hour talk, you have at best 1 point you can get across to the audience. And I would like that point to be that I'm running some training at Scala Sphere in Krakow on Thursday and Friday next week, where I will, amongst other things, explain the stuff in this presentation. So if you're interested, if this whets your appetite for finding out more, that Scala 1 training is running in less than a week, and tickets are €800 and there are seats available. And anyone here is most welcome. So let's start with something really, really easy, a list. A list is a value which can contain other values. Is everybody okay with this so far? Good. And that's what it might look like at the value level. But we can lift that to the type level. We can have an HList. How many people here have not used HLists? So you've all used one person. So you've all used HLists. Sorry, I'll explain them anyway. So we have an HList which will join three types, X, Y, and Z, together into a type that represents a list of types. So we've gone from value representing a list of values to a type representing a list of types. That is an HList. It's composed of hcons and hnil. And the structure, once it gets desugared by the compiler, will look a little bit like this, which is actually very similar to how the list looks like, the value level list. All okay so far? There is the definition of an HList. And you'll notice that it has an hcons and an hnil, which are subtypes of HList. And hcons is parameterized on h, which is the head type, and t, which is the tail type. So that is the definition we are working from. And we could ask the question, how do you check if a value is an element of a list? I'm talking about values here. And the solution would be to write a recursive function. And you've probably seen something like this before, def contains, where we take a list, we take a value, and we're going to return a Boolean, which will be true if that value is in the list, and will be false if it's not. We match on the list. If it's an empty list, well, the value obviously isn't in there, so we return false. If it is in the list, then we deconstruct the list into a head and a tail. And if the head literally is that value we're looking for, then great, we found it, we return true. Otherwise, and only otherwise, do we recurse on the tail. We call the same method to check whether the element's in the tail. So this is pretty simple functional programming. How do you do it for an HList? So we're at the type level now. So the solution is kind of the same. It's to write a recursive function, but to do so at the type level. And at the type level, we don't have the luxury of some of the luxuries we do at the value level. So we must implement things with types, and we can also use implicits, which are one of the tools we have available for calculating these things. And one big difference is that we can equate truth, the value true, to the mere existence of an appropriate implicit. So true is successful compilation by virtue of finding an implicit, whereas false is the absence of the implicit. And if the implicit is not found, then that is a compile failure. So that is a difference that distinguishes between value level and type level. So let's start by creating a type, and we'll call that type contains. That's going to be a type class that represents whether an HList contains a certain type. And we will demand this type as implicit evidence anywhere we want to check that constraint at the type level. And we'll make it a type constructor so it looks a bit like a function. So there is the function for reference, and there is the corresponding trait that we're going to use. You can see that whilst the the method there takes a value and a list. Our trait at the type level now has a type parameter for the value, which I'm calling v, and a type parameter for the list that may or may not contain that v. And what we want to happen is for this to compile successfully only if our list L, our HList L, contains the type v. So we need to write some implicits that will decide whether that type, whether that instance actually exists. So let's look at the base case. The base case is HNil, the empty list. And that certainly does not contain the type. It's false. And what do we do with false? We don't provide an implicit. So this is the simplest implementation you'll ever see. It's no implementation. You simply don't provide the implicit that you've dealt with the base case. That's done. Let's look at the inductive step. So we want to check if the tail contains the type or the head literally is the type. And we have to deal with an or here. We've got two alternatives. And we're going to use different implicits for dealing with each of them. This is something we have to do when we're working with implicits because we don't have the syntax to say this type or this other type. And let's say we'll check the head first. Seems a reasonable thing to do. And if that fails, we will check the tail. And we can use implicit prioritization. We can prioritize our implicits so that the first one will check the head. That will return an instance of contains, saying that the head type is in the list. If that list is an hcons, so that's excluding the case where it's hnil, but if that HList is an hcons starting with the head, we don't care what the tail is, but if the head is there, we're done, and we can provide the evidence. Now, the evidence you'll notice is null. That doesn't mean false, that means something. And actually, we don't care what that evidence is. We just care that there is something. We can implement this, we can provide this contains value with any value because we're never going to look at it. We just need to know that it's there. So we use null. But if this doesn't, if this doesn't infer the right type based on H and L, because the L is not matching this constraint here, then this implicit is not the solution. So what the compiler will do is it will look in the supertypes of this companion object. It'll look in the lower priority trait. And we have another implicit here. Now this one will return exactly the contains type class instance we want. So we're looking for L containing V, but only if that implicit can find another implicit. So we failed to match the head, so this implicit will provide the right evidence if the tail contains that value. So this is recursion. This is doing the recursive step. It's failed to find the head, so it looks at the tail. It uses these type parameters here to deconstruct the L into an hcons of H and T. T is the tail, and we go off and recurse on implicit search to find that, hopefully find that contains. And what we can then do is we can check whether, for example, string is contained within the HList int double string hnil. It will recurse a couple of times before it gets to the string being the head. Then it will find that head implicit, and then it will return and unwind. So that implicit has been found. All is good. But everything's more verbose. There is more code here to do something that in theory is quite simple at the value level. It relies upon implicit search. That's, I think, quite well known for being slow in the Scala compiler. And it has linear complexity. You probably wouldn't choose a list as your data structure for checking whether something is contained within it. You would probably want to use a set. So let's think about how we can lift sets to the type level. And I'm going to start by telling you the solution, which is to use intersection types, because these have behavior that is very similar to sets. If you've encountered product with serializable, which is an intersection type, that type is interchangeable with serializable with product. you can swap the two. They are considered identical types at the type level. Now, the implementations may be different. When you actually use them at runtime, they may have different, they may produce different values, but at the type level, we're only concerned with those types having properties, and properties are the existence of methods with certain signatures. And these two types will have identical signatures, and they are effectively identical types. We can also do deduplication, because the type A with B, with A with B, with C, with A with B, whatever else, is interchangeable with A with B with C. We can remove duplications. And this is exactly what sets do. Sets deduplicate, and they have no relevant order. So intersections look like they will be useful. And we can do a subtyping check. We can say that A is a supertype of A with B. Likewise, B is a supertype of A with B. And it's actually a supertype of itself, because every type is a supertype and a subtype of itself. And this is very similar to set membership, or that contains, or subset notation. The set A comma B contains the set that contains A. Likewise, B, and although it's not a proper subset, it is a subset. So this looks kind of similar. So we can use subtyping as a proxy at the type level for a superset operation. But this probably sounds a little bit backwards. We're equating superset with subtype, or supertype with subset. This is sort of the wrong way around. And there is the evidence. We have the arrows pointing, well, this is the subtype on the left, and this is the superset on the left. So that messes with my head a little bit. So there's a solution, which is just to wrap it all in a contravariant type constructor. That minus there makes this contravariant, and it reverses the polarity of subtyping. So that's exactly what we want to do. So now H set of A is a subtype of H set of A with B. And that looks, I think, more natural. And we can do this without using any implicits now. We can write a contains method that will only allow you to call it with types that meet some conditions, such as the set being a superset of the set containing the value you want to check. So this will compile because string appears here, because H set of string is a subtype of my set, which is the criterion that is there. So that's been met. If we had symbol or double there, that would not compile. So that is good. We can write this in a number of different ways. This is with the values specified there as well. But we could also use implicit evidence, which defers the check until later. Or you could actually switch your contravariants back for covariants, and you could write it in this way with two separate parameters where you provide the value first, and the H set must be the right type, such that the V there is a sub or supertype, one of the other, doesn't really matter, do what works. This is how you do type level programming. You check obvious cases, and if it works, all is good. So this is almost everything about H sets, but we have this. This is true. H set of exception with string is a subtype of H set of throwable. Does anyone know why? Well, exception inherits from throwable. So exception is a little bit like throwable with like some other details that make it an exception. So throwable is sort of artificially in this intersection, and we didn't put throwable into this intersection, so we don't really want to be told that throwable is in our intersection, or any ref. These are all in this intersection. This is undesirable. So we want to remove those subtype relationships, and the way to do that is to wrap all the elements in an invariant wrapper. So I'm going to put them inside HLMs, and that removes any relationship between HLM of exception and HLM of throwable. HLM of exception and HLM of throwable, by virtue of invariance, are unrelated types. There is no supertyping or subtyping relationship between them. So we're using that invariance as a tool. It's a bit more complexity, but we have made, we have got the condition we wanted that these should not have a relationship anymore. And this is now false, this check here. So one more thing with H-sets. What about the empty set? How do we deal with that? Is it H-set of nothing? Is it H-set of any? Well, both of those are problematic. What about H-set of H element of nothing? Well, that doesn't work because that's sort of putting nothing into our set. We don't want nothing. We don't want an element which is nothing. So that's not the answer. The solution is to split our HLM into two parts. Either it's an H value or it's an H0. H0 is always in the set. We're just going to say that we will always have an H0 in our H set, and H value will wrap each of the elements. If you have multiple H0s, they will deduplicate. We don't care. It's just there as a sort of placeholder. A bit like nil is a placeholder in a list. It doesn't represent any elements, but we always have to have one at the end. So it's the same sort of thing. And I'm going to define these type aliases. I'll leave these on the screen for 5 seconds, and you can absorb them. Got it? And that means we can use this syntax now. And this is quite nice. So we've removed a lot of the syntactic nastiness of having to wrap everything. And we can write an H set, which is type level set of the types that it contains as something like this. And we just use this tilde, which is a bit like it's the empty element. And it always has to be there. It always has to be on the left as well, actually. So how would we use this in something a little bit more practical? This is all a little bit philosophical. Let's say we want to add a greeting to a set. We want to add a string. And we're going to take an H set to begin with, which will have some abstract type in. This is an abstract type representing the elements that are in that set. And what we're going to return is going to be an H set of the same values, or the same types, and additionally string. And that's how we write it. And the implementation is not very interesting. I don't care much about values, but that is the return type we want. So let's say we started with an H set like this, and it has the type H set of int or int and string and double. I should have used and really, shouldn't I? Int, string, and double. And we're going to try to add the greeting. Now, maybe there's a problem here, because our set already has a string in it. I don't want to clobber a previous value that was in there. So my solution to this is to make sure that when we add that string, or when we append any new type to the H set, that we produce a new type which is different from the previous one. Now, if you add a string to an intersection that already contains a string, the type is identical before and after. So that's not what we want. We want to avoid that. So we want to ask for implicit evidence that they are different, that LMs and LMs with V are different. So we need to have a type class which only has instances where the types are different and not where they're the same. And this is something that Miles Sabin came up with many years ago, in fact, which uses implicit search again, and it uses a few quirks of implicit search. And it says the way implicit search works is that if it can find an implicit in the highest priority scope, if it finds two implicits in one scope, it will find ambiguous implicits and it will refuse to compile. And it won't even bother, it gets angry and won't even bother checking for later scopes to see if there's an appropriate implicit there. Whereas if the implicits don't match at all, so if these don't match rather than being ambiguous, it will then go and check a later scope. So in this case, if T1 equals T2, these two will both match, and they will instantaneously be ambiguous, and we'll get a compile error, and it won't bother checking here. Whereas if T1 does not equal T2, then T1 does not equal T2, then it will skip over these without even checking, and it will go straight to this one, which will always provide a result. So we only have a different instance if T1 does not equal T2. Okay, let's think about H-maps. Type-level maps. These are actually a little bit like sets. They're sets of key values rather than just values, or key types, I suppose you could say. We can define a couple of type aliases like this, and we can get this reasonably nice syntax here for an H-map. But we're going to use another feature of Scala, and I'm only going to give you a really superficial view of this, because we're packing a lot into the time. Unification. This is, I think, one of the least valued parts of the Scala type system. It happens all the time. For example, if you're expecting a list of t and you provide a list of int, the compiler is able to solve that. I mean, it's quite obvious that t equals int for this particular example, but the compiler will solve it using an algorithm that gets a little bit more hairy when it has more complicated types to work with. It's applied very frequently, and one of its best features is that we rarely have to think about it. But it's not complete. It doesn't always produce an answer. So given an H-map with some key values, we would like to get a value, or get a value of a certain type out. So we can ask for something by its type key, K. And we will expect to get a result back of some type V. I'm not going to show you the implementation because it's a little bit more complicated. But what the compiler will allow us to do is we can ask for a string, and through unification, it will dive into this type here, which is an intersection type. It's an intersection of key values, and it will pluck out the one that matches the string as the key here, and it will effectively ignore the other two parts of it. And having plucked out this type here, it can then use the double, which can make the return type. So I'm not showing you the implementation. This is just a tantalizing idea that you can do, and I've done it before. The implementation is actually kind of complex and very subtle, but this is something that the type system is capable of doing. Okay, how about H-trees? Well, what is an H-tree, or what is a tree? Let's answer that first. A tree is either a branch, which is a set of trees. These aren't binary trees, these are arbitrary-sized trees, or it is a leaf. So what is an H-tree? Well, we just translate that up to the type level. An H-tree is either an H-branch, which is an H-set of H-trees, or an H-leaf. And I'm not sure about the legitimacy of just sticking H in front of everything and making it the type level, but that's what I've gone with. H stands for heterogeneous, or sometimes heterogeneous, depending on who you ask. And I'm not sure what a heterogeneous leaf is, but we're going for consistency here rather than correctness, whatever that means. Anyway, we can define an H-tree like this. I'm not going to talk about what the details are, but note we have contravariance again here, and a really nice property of this is that if you can write an H-tree, if you can bring yourself to describe an H-tree at the type level, the subtyping relationship between two H-trees is the same as a subtree relationship. the compiler will, it's probably like an n cubed complexity algorithm, but the compiler will check all of the depths of your intersection types within intersection types within intersection types. And if there is a subtree relationship, actually it's probably n to the n, it's n to the n, or n to the depth complexity. It's horrible, but it will work. That is something you can do at the type level, but you shouldn't. What about directed acyclic graphs? What is a directed acyclic graph? Let's look at the value level first. A DAG is a set of nodes and a set of arrows between ordered pairs of nodes. So let's try and lift that to the type level, but it's complicated, and I have 4.5 minutes left to try to explain it. What is a node? Let's try a simpler question. Let's deal with one part of the graph at a time. A node is a value and a set of references to incoming nodes, or from incoming nodes. So let's try and lift that to the type level. An H node is a type and an H set of references to incoming H nodes. So let's write it very simply like this. This is going to be an intersection type. Maybe it wants to be contravariant again. Let's not worry about that too much. This is something new, ref of H node. We want some sort of way of representing a reference. And this seems like a perfect opportunity to look at singleton types. Singleton types exist merely by virtue of an identifier existing in a certain scope in the compiler. A stable identifier has to be a val, or a parameter to a case class, or a parameter to a class, or a lambda parameter, something which is never going to change, not a def, not a var. It is a type with only one member, which is that value itself. And they actually make very good references for our purposes of constructing a DAG at the type level. This is what I do in the morning. I wake up. I brush my teeth if I've woken up. So the wake up node is a dependency of brushing my teeth. I don't brush them before I wake up. I don't get dressed before I wake up either. And I go to work when I have both brushed my teeth and when I've got dressed. This is very important. If any of those is missing, then I have a problem. One is more important than the other, in fact, but let's not think about this too much. I didn't hear that. Well, you tell me later. Now, what if we wrote this instead? What if I tried to construct this type-level DAG? Can anyone see the problem? I have a reference to get dressed as a dependency of going to work that is a forward reference. It points to this get dressed type here. That is not permitted in Scala. You can't use a singleton type based on a stable identifier that hasn't been introduced yet. Compile error. And what I find really nice is that we have a seemingly unrelated compile error. It's relating to the order of construction that we're trying to refer to an identifier that doesn't exist yet, that is stopping us from doing something which could potentially allow a cycle in our DAG. That is not permitted in a DAG. It's acyclic. So an unrelated rule in the compiler is stopping us doing something which it's constructing a state which should not be representable. So I find that kind of cool. So just to wrap up, I should ask the question, maybe I should have asked at the beginning, but I'm asking it now. Why are we doing all of this? Because it is genuinely more complicated than the things you're familiar with at the value level. So why bother? Well, with these precise representations of types, we can work more with total functions. We can avoid partial functions. We can eliminate whole classes of errors that may occur when we have partial functions. The complexity, and it is complex, and I don't deny that a lot of this is somewhat magic, but all that is in the definitions. It's all at the definition site. At the use site, you get compile errors when you try to represent states that aren't representable. And we can write it once. We can put all the fun and love into writing it once, making it work, and then we can just use it many times without needing to worry about the details. So I don't expect everyone to have followed everything or maybe even anything in the talk. but thank you for coming. I hope I've shown some of the potential of the type system in Scala, some of the weird and wacky things you can do. And there we are, we're okay. And I hope you sort of go away without believing that working at the type level only really means manipulating HLists with recursive implicits. It doesn't. Dave's on next, but I think you're not talking about manipulating HLists today. No. If you want to manipulate HLists, ask Dave. But for now, I'll just finish up by saying that I know everything looks like a magic trick. It looks like some random combination of features I've plucked together to just make stuff work. But it is possible, with the right familiarity, to think about these concepts very logically, very naturally, to compose them in ways that are that make it very natural to use them as tools to do tasks you want to do, to search for variants, to use implicits at the times where you need them. What people lack, and what it is possible, I promise, to learn, is familiarity with these so that you can do that. And of course, please consider coming to my training next week. It's not far away, it's a short train ride, and the website is there. Thank you, everyone. I hope it hasn't been too difficult to understand.